Question 13 from the 2024 Higher Physics Examination from the SQA, Section 1. The following statement represents a nuclear reaction, and we can see the nuclear reaction there. The total mass of the particles before the reaction is 26.572 times 10 to the minus 27 kilograms, and the total mass of the particles after the reaction is 26.560 times 10 to the minus 27 kilograms. And we're asked to find the energy released in this reaction. Well, as you can see from the mass before and the mass afterwards, there's missing mass there, and that missing mass has been changed into energy according to Einstein's famous formula, E equals mc squared. So all we have to do is find the value of that missing mass, multiplied by the speed of light squared, and that's just got the energy. So let's take the mass before. It's going to be 26.572, and it's going to be times 10 to the power minus 27 kilograms, and we're going to subtract from that the value of 26.560 times 10 to the minus 27 to find the missing mass. And we do that sum there. You can see we just keep the times 10 to the minus 27 kilograms in there. We have got this part here is going to give us 210. There's the decimal point 0. So there's the value of the missing mass, 0.012 times 10 to the minus 27 kilograms. So the energy equivalent of that is going to be E is going to be equal to the mass, the missing mass, 0.012 times 10 to the minus 27. I'm going to multiply that by the speed of light squared, 3 times 10 to the power 8 all squared. And we do that in a calculator, we end up with a value of 1.08 times 10 to the minus 12 joules. If we do that in a calculator. So that missing mass, the energy released will be 1.08 times 10 to the minus 12 joules. And we look at the responses, we can see that we're going to have that answer there, answer D. Question 14 from the multiple choice of the 2024 Higher Physics paper. A student carries out an experiment to investigate how irradiance of light varies with distance. A small lamp is placed at a distance d from a light meter, and the radiance I at this distance is displayed on the light meter. This measurement is repeated for a range of different distances, and the student obtains these results to plot from the graph. Now the graph indicates that there's a systematic uncertainty in the experiment. Which of the following alterations could most likely to reduce the systematic uncertainty in this experiment? And we're given 5 options. One option is to repeat the experiment in a darkened room, B, repeating the readings at each distance to calculate averages and decreasing the brightness of the lamp, D, replacing a small lamp with a larger lamp, and E, increasing the range of distances. Now the clue is a systematic uncertainty, and we can see that we're very far away from the lamp, because remember 1 upon d squared, if we're very far away, 1 upon d squared is going to be equal to about roughly 0 here. We're still getting some irradiance here, and the graph is going to start there, not at this point here. So that must mean that there's some sort of light source which is infecting our experiment, which is causing a systematic uncertainty. So the answer for this question is to repeat the experiment, but put it in a darkened room. Perhaps maybe there's some light being reflected off something. Perhaps there's maybe a window which is letting in some light, and that's adding to this uncertainty and giving this extra little bit of irradiance when we're quite a distance away from the lamp. So the answer to this question is A. It is repeat the experiment in a darkened room. Question 15 from the 2024 multiple choice paper from the SQA. A group of students make the following statements about coherent waves. Statement 1, coherent waves have a constant phase relationship. Statement 2, coherent waves have the same frequency. And 3, coherent waves have the same speed. Which of the statements are correct? Well, we know for waves to have coherent waves, they have to be travelling at the same speed. And they also have to be travelling at the same speed, but they also have to have the same frequency. And they have to have the same constant phase relationship. That's always a kind of harder one to explain, because people don't really understand what constant phase relationship means. And the best way to describe that is to look at the hands of a clock. So if I bring in these two simulations here, you can see that the top one is out of phase. Those two hands are out of phase because one hand, the red hand, is being caught up with the blue hand. So these two clock hands are out of phase. But if we look at the bottom picture, we can see that the two waves travelling along keep the same time apart. They keep the same distance apart, if you can think of it that way. And in terms of wave language, this wave here is in what we call a constant phase difference. The difference between the red hand and the blue hand is always the same. So that's what we mean by a constant phase difference. This set of waves have a constant phase difference. This set of waves hasn't a constant phase difference. So to be a coherent wave, you must have a constant phase relationship, you must have the same frequency, and you must have the same speed. So the answer is 1, 2 and 3, which is going to be E for your answer.